Hello, and welcome to our video covering topics in section 2.4. In this video, we will begin by looking at the inverse of a function. Then we will use that to understand the inverse of a matrix. And then we will look at some criteria for determining whether a matrix is invertible. And then we will end with the algorithm for calculating the inverse. So, all right, let's jump right in. What's the inverse of a function? Let's remember. Okay, this isn't actually going to be putting any fun in function because I'm even just starting with the definition. I don't know why I thought I'd get your hopes up. Okay, so yeah, a definition. So a function f from the set x to set y is a relationship that maps each element of x to exactly one element of y. So that's the definition of a function, is this idea of mapping or sending each element of your domain to exactly, each one gets mapped to exactly one element of your codomain. In pictures, which is always easier to think about, let's look at something like this. Okay, so we've got our set x, our domain, and our set y, our codomain. And now our job to determine if we have a function is to say, well, is each element of x getting mapped to only one element of y? And it is. I mean, really, in this picture, the question is there only one arrow coming out of each element of x? And it is. In an example like this, which sometimes trips students up, here, all right, we have each element of x still gets sent to only one element of y. Each one is paired with only one element. It's a little confusing because x1 and x2 are sent to the same y, but that's okay. Where it's still a function because kind of this idea of like each arrow, there's only one arrow coming out of each element of x. So this is a function. Now what about this? Okay, here we're not hitting every element of y. y0 is not getting hit. But this is still a function because each element of x is only going to one element of y. So these are all functions. Okay, now let's talk about invertible functions. They're special kinds of functions. So by definition, a function from a set x to a set y is invertible if each element of y had exactly one element of x mapped to it. So again, let's look at pictures. In this first example, all right, is it the case that every element of y only had one element of x mapping to it? Yeah. Here the idea is kind of like if you reversed the arrows, would it look like a function? And so yes, each one of these elements of y had only one element of x getting mapped to it. So that is an invertible function. But what about this function from x to y? Well, here, this y0 had more than one element mapped to it. And so this, by definition, is not a function. And how about this? Well, each element of y that has an arrow pointing to it has only one element of x pointing to it, but this y0 doesn't have anything pointing to it. And by definition, the function has to be invertible if every element of y has exactly one element from x mapped to it. And this has 0, not 1. So this is also not a function. Okay. Here's some facts about invertible functions. So first, if a function f from x to y is invertible, then there exists something called an inverse function. It's denoted f raised to the -1, mostly to just confuse students because this is already exponentiation to -1's already been defined, but I digress. Okay, it's invertible. If a function is invertible, then there is what's known as an inverse function. We denote it f raised to the -1, and that function, if the original was from x to y, now your inverse function is from y to x, and your inverse function is defined such that if f of x equals y, then f inverse of y equals x. So this is the idea like, oh, if the function takes x to y, then the inverse function takes y back to x. kind of this idea of like undoing what was done. It is true that the inverse function itself is invertible. So if you like go back and stare at the definitions long enough, I think you will be able to convince yourself that the inverse function, one, actually is a function, and two, is invertible. And in fact, its inverse is your original f. And the whole kind of idea, practical significance of inverse functions is kind of wrapped up in these two equations, where you've got an element x. If you apply f, so f maps to some element of y, and then you apply the inverse, you get back your original x. Similarly, if you started in y and you applied f inverse, and then you applied f, you would get y back. So it's this idea of inverses undoing what you did with the function. So function, and then the inverse just gets you back where you started. Okay, so now let's use this to talk about what the inverse of a matrix should be by definition. So let's recall that a linear transformation, T, is a function that can be represented as multiplication by a matrix. So if you have some vector x, where does this transformation map x? Well, it takes it to whatever vector you would get if you multiplied x by the matrix A. So this is really like, okay, if we're thinking of matrices as functions through multiplication, then what should the inverse of a matrix be? Well, by definition, a matrix is said to be invertible if the linear transformation defined through this matrix multiplication, if that linear transformation is invertible. And then your book says, in this case, the matrix of the inverse transformation is denoted by the matrix raised to the -1. And let me pause right here and say that this sentence actually is assuming that the inverse transformation is always also linear, because this is saying, oh, if the transformation has an inverse, that inverse has a matrix associated with it. So that's assuming that the inverse is linear. And I guess I feel the need to convince you that that makes sense. And I think one way to do it is geometrically. So if you remember from that 3 blue 1 brown video, geometrically, a linear transformation takes straight lines to straight lines and leaves the origin in place. And so if you think about undoing the process, well, you took a straight line to a straight line. So if you're undoing it, that process, you're taking your straight lines and bringing them back to straight lines. And then leaving the origin in place means, okay, linear transformation maps the origin to the origin. And so if you undo that, you've once again you haven't moved the origin in the first place, so undoing it doesn't do anything either. So hopefully you're not worried about the fact that the inverse of a linear transformation can also be represented by a matrix. Another thing I want to say about this definition is that it's definitely technically true. It's probably not the definition you've seen if you have seen the definition of an inverse of a matrix, but this is a theoretically useful definition, but maybe not quite so practically useful. So let's look at an alternate definition. So here's something you may have seen before if you've encountered matrices. A matrix is said to be invertible if there exists some other matrix, we'll denote it A raised to the -1, such that if you multiplied A on the left by A to the -1, you would get the identity matrix. And if you multiply A to the right by -1, you would get the identity matrix. So if you have a matrix where some other matrix, both multiplying on the left and the right, gives you the identity, then your matrix is invertible. And this matrix that you get is called the inverse. Or the matrix, this A to the -1, that matrix is called the inverse matrix. And so I want to just motivate a little bit why this should be how we define an invertible matrix and what the inverse is. And so the motivation is that we'll notice, like, here's something we want. When we were talking about functions, we had, well, if we take x and apply f and then apply f inverse, we should get x back. And so similarly, if we have some vector x and we multiply by the matrix A, if there is an inverse, multiplying by the matrix A to the minus 1, that should get us x back. And similarly, if we had y and we multiplied by the matrix A inverse and then multiplied by A again, we want to get y back. This is like what we want. This is like our requirement of inverses, is that if you do them both, then you've done nothing. And so, well, but matrix times a matrix is a matrix. So what matrix should this be? It's got to be the identity matrix, because the identity matrix is the matrix that takes a vector and does nothing to it. So hopefully this definition, is reasonable. All right, so let's just get down some stuff that we know about matrices, or that we can convince ourselves is true about invertible matrices just from the definitions and what we already know. First, an invertible matrix has to be square. So let's think about a little bit why that has to be true. So let's think first just from R2 to R3 and back. So an invertible matrix, so if you had like a matrix or a linear transformation from R2 to R3 and then back, I'm claiming that you can't have, that it can't be, that you can't do it. You can't have an invertible matrix that does it. And maybe this is obvious to you, but it actually, I think, isn't that obvious. And one reason is that, this might be surprising, but there actually are invertible functions between R2 and R3. This fact is wild, actually. It's due to 19th century mathematician Georg Cantor, and in his quest to understand infinity, he proved there are multiple levels of infinity, which itself is wild. But then kind of a surprising result was that actually R2 and R3 have the same level of infinity. And if you take real analysis, you will prove that you can have an invertible function between these two. You'll define one yourself. Might even be a homework problem in that class. So that's crazy that actually there are invertible functions. And it turns out they just can't be linear. And maybe one other thing I'll say about this, just, like promoting other higher math classes, is that you could see this idea of the fact that there are invertible functions between R2 and R3 being worrisome and kind of being an impetus for this class called topology, or this field of mathematics called topology. I've heard topology sometimes motivated as the quest to recover dimension after Cantor's results on infinity. But anyway, okay. Can't believe you're letting me get off on these tangents. Point is, okay, maybe it's not obvious, but it is true that an invertible matrix must be square. And actually, the next couple things I will say, I think might motivate that. But here's another true fact. If you have a square matrix, it's invertible if and only if its reduced row echelon form is the identity matrix. All right, so why does that make sense? Should it be true that if a matrix is invertible, its reduced row echelon form should be the identity matrix? And I think it comes down to this idea of solutions, this more theoretical look at what an inverse is. So if you have, for any output, exactly one input, that means that if you had a linear system, then you only then if you have a unique solution, the system is invertible. And this condition here, that the reduced row echelon form is of A is the identity matrix, that is the condition for having exactly one input for every possible output that's out there. And so this maybe like can convince you that an invertible matrix must be square, because if you're thinking about having exactly one input for every output, what does the reduced row echelon form have to look like? Well, okay, if it doesn't look like this, then either you have no solutions or infinitely many, in which case you wouldn't have an inverse. Okay. Saying this same thing but in a slightly different way is to say that a matrix is invertible if and only if its rank is n, which is to say, okay, if the rank is n, then for every row and every column there's exactly one leading one, and in that case your reduced row echelon form is going to look like that. Okay, here's another kind of going back to the kind of theoretical thinking about solutions and mapping definition of invertibility. This says an n by n matrix A is invertible if and only if, given some constant vector b in Rn, then the equation ax equals b has a unique solution x. So this is saying, all right, if you have some output, exactly one x, one input would get you there. So yeah, this is basically just another way of stating that theoretical definition of invertibility. And then this says just, okay, well, that x, you can calculate it. It's A inverse times this vector b, which makes sense. You just multiply A inverse by both sides, and then you'd get x here and A inverse b on the right. This last one actually is pretty theoretically useful. So, okay, that's some stuff about matrices. Let's use those facts to talk about some criteria for how can you tell, given an n by n matrix, how can you tell it's invertible? Well, here is your bread and butter check for invertibility of a matrix. Yeah, just find the reduced row echelon form and make sure that it's the identity matrix. This is a great system if you have a specific matrix that you're looking at and a computer handy to calculate the RREF for you. But this is actually not great if you want to prove things about matrices in general. If you want to do that, you might want a more theoretical check. So here's a theoretical check for invertibility that you would use in proofs. And this is theorem 2.4.4 in your book. And it says, matrix A is invertible if and only if the only solution to the equation AX equals 0 is X equals 0. So first, let's take a moment and think about the equation AX equals 0. It is always true that the 0 vector is going to be a solution here. Because take any matrix, multiply it by the 0 vector, you're going to get 0 out. So, okay, AX equals 0 always has a solution, and that solution always has at least one solution, and that solution is X equals 0. But if X equals 0 is the only solution, then our matrix is invertible. And actually, that's, it's certainly true that if the matrix is invertible, it has to be the case that X equals 0 was the only thing sent there, because that's our like theoretical definition. It's a little more interesting to think about why that's enough. You only have to check this one point. And it has to do with the fact that it's linear, but maybe I won't go into it. But I just will say this gets used. This will be used on the next slide, but also in more, just later on in mathematics, you're proving things in general. This happens to be a really handy theoretical tool. Okay, so here's your book actually lists some criteria for invertibility. So these are things to check, and it's sufficient to check these things to know that a matrix is invertible. So here it says if you have A and B, and they're both n by n matrices, and it's the case that B times A is the identity matrix. And then it turns out both A and B are invertible. The inverse of A is B, and the inverse of B is A. And A times B is the identity matrix. So remember in our definition of, in that alternate definition of the inverse of a matrix, we needed both, say, BA to be the identity and AB to be the identity. And here, this is saying, well, if A and B are both square matrices, then you really only need one of those conditions to be true. And then the rest is true. So let's, I think I just want to prove this A, where we say, all right, if B times A is the identity matrix, then let's just say, let's prove that A had to have been invertible. So proof that if B times A is the identity, then A is invertible. And we're going to prove that? I mean, it's not obvious how you would prove that. Certainly using reduced row echelon form or something, and it would be a little, it's not obvious. But we're going to use this tool that we talked about in the last slide. If we can show that AX equals 0 means that X equals 0, meaning like if this is true, then the only thing that made that true, you required that X was 0 all along. So if you can show this, then you've shown it's invertible because this was the criterion on our last slide. So, all right, let's start with AX equals 0. So suppose AX equals 0, and let's see, can we prove that X had to be 0? Well, we only know one thing, and that's that B times A is the identity matrix. So multiply on the left by B. That gives us BAX for the left side and B0 on the right. Now B0, that is just 0, and BA is the identity matrix. But X times the identity matrix is just X. So okay, we've shown that if AX equals 0, X had to be 0 in the first place. Yeah, just a little theory dropped on you. So, okay. But in practical aspects, you may, in this class, be asked to calculate an inverse. And at this point, we've said nothing that would indicate how you would ever do that. So let's right that wrong. Let's recall this encoding position example from the start of section 2.1, where you've got like a ship leaving Marseille, and they are sending its coordinates are x1, x2, and they send an encoded coordinate system y1, y2. And the encoding was, they said, okay, let's take x1 and x2, multiply it by some, essentially multiply it by a matrix, and then you get this output y1 and y2. And then to decode it, the idea was, all right, you use elimination, and now you solve for x1 and x2. And if you remember finding like inverses in pre-algebra or, pre-calculus or something like that, you might remember just, oh yeah, to find the inverse, you solve for x. And so solving for x gives you something like this. And so this is just the basic idea for finding the inverse of a matrix. So let's matricize these, what we just did, to get an idea of what we should be doing in general. So, all right, how do we matricize this left side? Well, okay, we've done this a million times. We've got some coefficient matrix, 1, 3, 2, 5, and then we have on the right side, this may be like, you might have expected just, putting y1, y2 here. But actually, we're thinking of y1 and y2 now as variables in their own right, and so they should each get their own column. And so since we have one y1 and one y2, and they're each in their own column, we represent the right-hand side like this. And then to decode the system, well, we're solving for x and y, we're solving for x1 and x2, which means we should find the reduced row echelon form, and that will solve for x1 and x2. So we refify this augmented matrix. I know you guys probably thought I was done with this gag the last time. I'm not. Anyway, okay, so you refify. And now on the left side, you've got the identity matrix. And on the right side, you have this like decoding matrix. And it turns out, okay, if your original coefficient matrix was A, then the matrix you get on the right-hand side after finding the reduced row echelon form of the augmented system, that right-hand side is the inverse. So let's say this in general. To find the inverse of a matrix, what you do is you make that matrix the left side. So matrix inverse, if it's invertible, it had to be n by n in the first place. So make that the left side of an augmented matrix. Make the right side the n by n identity matrix, and then compute the reduced row echelon form. If you do that, and you get something that has the identity matrix on the left side and some other matrix on the right side, then you know that A is invertible by our, that bread and butter test. The reduced row echelon form ended up being the identity matrix. So A is invertible, and the inverse matrix is B. And I think in the next video, we'll actually go through an example of calculating this by hand. All right, thanks for watching.